Okay, so let's go ahead and get on with section 4.3. Section 4.3 in your book, I think, is titled something like the derivative and how it affects the shape of the graph. But really, the majority of 4.3 and what it introduces is f double prime, the second derivative, and how that impacts the shape, what that says about the graph of f. Okay, so what 4.1 did for the first derivative, 4.3 is going to do for the second derivative. Okay, now we've already talked about the second derivative just a little bit, and we know that. And let's go ahead and just make it with respect to physics. If f is the position function, we know that f prime is the velocity function, and what we're usually used to thinking about in terms of the graph as slope, right? Now f double prime is, of course, the second derivative of f, but it's the first derivative of velocity, so it's the rate of change of velocity. And that, of course, is going to be acceleration. So even when we're not dealing with something that is specifically physics related, or dealing with something involving particle motion or gravity or something like that, it's still helpful to think about it in these terms, because even if it's not specifically position, velocity, acceleration, it will be analogous to that relationship, right? Because velocity is the rate of change of position, and acceleration is the rate of change of velocity. Now the question is, we know that how f prime describes the graph of f. What does f double prime describe? And that, of course, is the big question. So let's go ahead and look at two examples of something, of a function. Let's look at this function, and let's look at that function, okay? Let's say that that is the right-hand side of y is equal to x squared, and that is the right-hand side of y is equal to root x. Now, they're both increasing functions, okay? They both have a y prime that is positive, right? They're both increasing on that interval that's shown. Each successive value of x gives you a successively higher or greater value of y, and therefore that's what it means to have a positive slope, right? As you go right, the graph goes up, okay? Well, that's the same over here. As you go right, the graph goes up, but those are definitely different shapes, okay? Now, whereas, and we're not going to think about, let's stop thinking about the outputs and let's start looking at the way that the slope behaves on this. We see the fact that the slope right here at the origin is 0. The slope right here is positive, okay, but moderately so. The slope right here is more positive, or a greater positive value. So you can see the fact that the velocity as you're going this way on x is positive, but the velocity is increasing, okay? So if the velocity is increasing, we should know just very, very easily from physics, or just from common sense, that if the velocity is increasing, you're accelerating, okay? Acceleration is positive, and therefore the second derivative is positive. Now, this has positive slopes, but each successive slope, as you go right here along the x values, is going to be positive, but less so, right? Positive getting less positive, or positive getting more zero or flatter, okay, according to the general shape of the graph. And therefore, it's slowing down. The velocity is positive, but the acceleration is negative, okay? So y double prime talks about basically whether it's positive getting more positive, whether the slope is positive getting more negative or less positive, whichever way you want to talk about it. And of course the same is true for negative slopes. It can be negative getting more negative, or negative getting less negative, or more positive, okay? And let's go ahead and look at, let's go ahead and put it into a nice neat little chart, because sometimes that helps us sort of distill the information that's been given to us so far, as much as I, sometimes I'm allergic to that sort of thing. Let's go ahead and just make ourselves a nice neat little chart And let's say this is where y prime is positive, and this is where y prime is negative. This is where y double prime is positive, and this is where y double prime is negative. Now, we've already seen both of these scenarios. If it's increasing, it goes up. If the acceleration is positive, it looks something like that, okay? So this is positive acceleration, positive velocity. So positive velocity, negative acceleration looks something like that. Okay, well, let's talk about negative slope. Negative slope looks like this, but if it's positive acceleration, it's negative slope getting less negative. Okay, so the slope is negative, but as you go to the right, it's getting more zero-ish, okay? And so that would be negative slope getting less negative, okay? And then, of course, we need to talk about negative slope getting more negative. Negative slope getting steeper in the negative direction. Now, when you think about it, these are really the only four ways, if your graph curves, to really talk about the curve of a graph, okay? And let's actually go ahead and look at an example that displays all four, okay? And it's really not that hard to find one. A full period of the sine function will do for us, okay? Because we notice that we can divide this into four subsections, and each of those subsections has a very different look, okay? In this first section, from 0 to pi over 2, because if this is the parent of the sine functions, this is 0 to pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi, right? This is a full period, and it's periodic, so it'll continue as it goes forward. This right here, you know that y prime is positive because it is an increasing function on that interval. And you know that y double prime is negative, okay? Because that slope is positive and getting less positive. This portion right here from pi over 2 to pi is y prime is negative, okay? And therefore, but you also know that it's negative getting more negative. So acceleration is still negative, okay? On this portion of the graph, you have negative slope getting less negative, right? The slope is going towards 0, which it actually will occur right here. So the slope right here is still negative, but the acceleration is positive, okay? And over here, we see the fact that the slope is positive, and the acceleration is what? Well, the acceleration is positive because that's positive slope getting more positive, right? And anytime positive slope gets more positive, it's kind of like you're stepping on the gas in the car, okay? Now, when we talked about first derivative, we basically labeled extrema, right? And we know from the first derivative test that this right here is a maximum point. It is a maximum point and can be designated thus by the first derivative test because it's there where the first derivative changes from positive to negative, right? At that point, it changes from positive to negative. And down here, and just kind of it changes, the slope changes from negative to positive. So you have a minimum point right here. Well, what do you call this point right here where the acceleration changes sign? Because notice right here from 0 to pi, the acceleration remains negative for that whole interval. And over here, the acceleration remains positive from pi to 2 pi. Well, there actually is a special name for that particular point right there. That particular point is called a point of inflection, okay? So we have a point of inflection. Well, thankfully, unlike the first derivative where you have two different types of points, where a critical value can be either a maximum or a minimum, where the second derivative tells you that there is a change in sign of the second derivative, that is merely a point of inflection. Now, When we talk about maximum and minimum points or points of inflection, the flip side of all of that, or the other side of the coin, so to speak, is the fact that we basically have a description of the intervals that occur between those points, right? So if your interval is simply 0 to 2 pi, how do you, in terms of the first derivative, describe this interval from 0 to 2 pi? Well, it has a positive slope, and therefore it is an interval where the function is increasing, right? And you have an interval here from pi over 2 to 3 pi over 2 where you have negative slope the entire time. That interval is where the function is called decreasing. And then, of course, from 3 pi over 2 to 2 pi, you have increasing. Okay? Now, you also have, when you find these points of inflection, that also carves up your interval into what's called concavity. This is concave down, since it actually looks like a cup that's pouring water out, right? And this is concave up, right? So if it looks like a cup, which is upward facing, where it would actually, hold water, it's concave up. This right here is concave down. And you can see that at this point right here, this graph changes concavity. Okay? So basically what we're doing is now we're taking our knowledge of the first and second derivative. First derivative describes slope. Second derivative describes what we're calling concavity. And we're basically trying to designate the points at which increasing and decreasing change, or we're trying to find the point at which concavity changes. So the first derivative will give you those points at which your increasing and decreasing intervals change. And the second derivative will give you points of inflection where concavity changes. Okay, well that's all well and good until such time as we actually get to an example. So let's go ahead and get to an example, and I think everything will wind up being all peachy and stuff, okay? Now let's go ahead and let's just do a Mickey Mouse training wheel sort of question. Let's do a polynomial. Let's say we have g of x is equal to 3x squared minus x cubed. And let's say I want to find everything that I know how to find about that. Okay, well, first of all, let's think back to our Algebra 2 knowledge. You know what that looks like. In fact, you could actually, negative x cubed plus 3x squared, or if you wanted to, you could have factored out the x squared, and that could have been 3 minus x, okay? So you already know that that's going to have a 0 at 3, it's going to have a 0 at the origin, and that 0 at the origin is going to be a 0 of tangency, because it has a multiplicity right there. So if it has a 0 of tangency right there, that's obviously going to be a maximum or a minimum point. You happen to know that this is a cubic function with a negative leading coefficient. So you could actually, if you really wanted to, go ahead and draw that right there, okay? Now you happen to know that it's going to look something like that, right? And you knew that back in Algebra 2. So you know that you're going to have a minimum right here, you're going to have a maximum right here, somewhere between 0 and 3. Well, that's good to know right from the outset, but let's go ahead and apply our calculus knowledge. So g prime of x is going to be 6x minus 3x squared, which is, of course, 3 times 2x minus x squared. Actually, let's go ahead and pull out the x as well. So that's 3x and 2 minus x. So my critical values are going to be x is equal to 0 and x is equal to 2. Well, I'm so glad. Let's go ahead and do a first derivative sign chart. I know that that chops my domain up into 3 pieces. Okay. And I know that at x is equal to 0 and x is equal to 2, that derivative function is 0. Okay. And I know that I can actually find, and we don't need the original g prime as long as we have the factored form right there, we know that g prime is going to give you values here. Now I happen to already know the shape of the graph, so I can predict it, but let's go ahead and plug it in anyway. Let's take a representative value from this interval, let's say -1. If I plug in -1 here, I get a negative. If I plug in -1 here, I get a positive. So that's negative times a positive or a negative. Let's plug in positive 1. If I plug in positive 1 right here into this factor, I get a positive. Positive times a positive is a positive. Let's take a representative value from this interval. Let's plug in a 3. I get a positive and a negative. So that's going to be negative. So I know that my graph looks something like that. Well, I already knew that, but the first derivative sign chart is always instructive, right? And so from there, I can actually designate that as a minimum point and that as a maximum point. And the great thing about the sign chart is if I'm asked for intervals increasing and decreasing, I already have it in interval notation. My decreasing intervals are negative infinity to 0, union 2 to infinity, and my increasing interval is going to be what's left, 0 to 2. Well, let's go ahead and do the second derivative, because that's what's actually new to us, okay? So the second derivative, let's go ahead and get back up here. I know that g of x was, let's see, it was 3x squared minus x cubed. G prime of x was 6x minus 3x squared, and g double prime is going to be 6 minus 6x. Okay, well that's 6, 1 minus x. That's really, really easy. Now, this is sometimes what's called a critical value of the second derivative, right? And just like the critical values of the first derivative, this is not necessarily a point of inflection. I have to confirm it using a sign chart and sort of the attendant logic, okay? So what I'm going to do is I'm going to plot that into a sign chart. And negative infinity to 1, x is equal to 1, and 1 to infinity. And g double prime of x is 0 at this point, okay? And I know that if I plug in 0 into here, that's going to be positive, so it's going to be concave up on that interval. And if I plug in 2 into here, it's going to be negative, and that's going to be concave down on that interval. So just like you designate a minimum or a maximum where you see changes in sign in your sign chart, you designate a point of inflection where you see a change in sign in your sign chart. Okay, so you would actually go in, and actually this is the point 1, 2 if you plug it into the original, function. And you say 1, 2 is a point of inflection, okay, because g double prime changes sign from positive to negative. Now, of course, you wouldn't, be quite so sparing with your notation, and you wouldn't abbreviate it like that. You would actually spell it out, but you get the point. And of course, if you were asked for intervals concave up and concave down, you would say, well, it's concave up. Well, you already have the interval listed out here from negative infinity to 1, and you know it's concave down, okay, from 1 to infinity. And of course, all of that winds up being very, very apparent from what we saw here, right? Yeah, this is just a rough sketch, but even from the rough sketch, we can see the fact that right there, right about at x is equal to 1, you see the concavity change from concave up to concave down. Now, from the multiplicity, we already knew that we had a minimum right here because it was a 0 of tangency. And we can even see from our rough sketch the fact that we had a maximum right here at x is equal to 2. So our Algebra 2 knowledge basically gives us the confirmation that all of my analytic work with respect to my calculus was actually dead on, okay? And so that's why I'm saying that, just because you have these new tools to use in terms of the analysis of graphs of particular functions doesn't mean you need to forget what you know from Algebra 2 and Pre-Cal. In fact, you just need to lay it on top of that and have it expand and enrich the knowledge that you have of functions already, okay? Now we're getting towards 20 minutes, so I'm going to end this video here. But now that I've done the explanation of exactly, at least what the large part of 4.3 is about, we'll get on towards more examples in the next few videos.